Hi and welcome to the video lecture series on thin film flow modeling and simulations in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Algust and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the sixth and last part of the second video lecture on the introduction and underlying theory, and here we'll present some examples of solutions to the Reynolds equation. Let us consider now a 1D infinitely wide slider bearing so that we have a 2D flow problem and a Reynolds solution to a 1D lower dimensional Reynolds equation. So what we have here is a moving lower surface and a stationary upper surface, and you can see that the lower surface moves with the speed u1, and you can also see that the speed u2 is set to 0 of the upper surface. The bearing length is defined by L, and we have a boundary pressure which is PA, denoting and the A denotes that it's an ambient or atmospheric pressure if you like. And the upper surface has a wedge shape which is described by the angle alpha, and therefore the film thickness may be described as the clearance at the trailing edge H0 plus the tangent of alpha times L minus x. Notice that the clearance here has been extremely exaggerated, and the factor between the z and the x-axis is typically 1 to 100 or 1 to 1000. So in reality, the inclination is only a fraction of a degree, and the film is typically thinner than the diameter of hair, so less than 100 micrometer thick at the exit, at the trailing edge, but not so much more than at the leading edge because of the very small inclination. When we talked about the lubricant rheology previously, we already saw the X velocity depicted like this color map. But what is interesting to notice here is that there is a region of backflow here in the trailing edge of the bearing, and it can be seen, but it's not so easily seen at the color scale for the velocity that we have here on the right. There will be a hydrodynamic pressure buildup in this case where we have an inclination and if we have a viscous fluid. And this hydrodynamic pressure will in this case look precisely like this, where we have on both ends we have PA, the ambient pressure or atmospheric pressure typically, and then it builds up, comes to a maximum and drops down again to the ambient pressure at the exit. It of course acts on both surfaces, and this is what generates lift in a bearing or load carrying capacity in a bearing. And the load carrying capacity of the bearing is just the integral of the pressure that develops, but it's we have to be a little bit careful here. So it's the integral of the Z component of the pressure. But Pz is P cos alpha, and alpha is tiny, so it is more or less P. So therefore, typically when we talk about load carrying capacity of a slider bearing, we state it as F equals the integral of the pressure over the length of the bearing. And where does the pressure come from? It comes from the solution, or it is the solution to the Reynolds equation. Now, instead of having a fixed stator, we can think of the stator being guided here on a linear bearing. So it can move up and down and adjust its position in accordance to the applied load. And then the load carrying capacity is really a force equilibrium statement, saying that minus F, of course, because it acts in negative Z direction, must equal the pressure in the Z direction. But look here now, we have to be even more careful here. So I put a small prime on our Z component of the pressure. And that's because P prime itself, it's P minus the ambient pressure. So it's the net lift. And this is required since we also have typically the ambient pressure on top of the bearing also. So we need to subtract that, and because of that the angle, the inclination is so small, we can approximate Pz prime by P minus Pa. And therefore we can pose the force balance equilibrium equation precisely like this. Now this force balance is directly coupled to the clearance at the trailing edge here, for example, but the clearance everywhere, of course. So in reality, we don't know that clearance of the trailing edge. But we do know, maybe, or at least we can pretty easily or pretty accurately appreciate the bearing load F. The film thickness, in this case, since the inclination is so small, is only the trailing edge film thickness plus alpha times L minus X. So it's a linear slider, linear expression here, and alpha determines the angle of the inclination. We have the force equilibrium, and we have to be careful again. We have the net contribution. So if we want to find now the clearance H0, we can iteratively solve the Reynolds equation for different values of it, different values of the clearance, until we satisfy the force balance equation. And it turns out that there is an inverse relationship between F and the square of the clearance. And this can be easily found by stating the problem in dimensionless form. So the solution procedure to that would be, we have the Reynolds equation, we insert an initial guess of the separation, the clearance at the trailing edge. We compute P for that one. We check, is this pressure satisfying the force equilibrium? If it is, well, we're done. H, the real separation H0 is actually the one that we inserted. Typically it's not, and we must do this a few times to find it. So we update H0 based on the difference between F and the integral of the pressure. We insert this one, update the film thickness H in the Reynolds equation, we compute again and update, and hopefully we're now done. And this solution procedure can be implemented, for example, by means of the secant method. But in order to start the secant method off, you need two values of your initial guess, and these ones can actually be obtained from an interval halving method, which is very stable. But there are various fixed point iteration methods to be applied to solve this problem for us. Okay, so inclination is small and load carrying capacity of bearings is large, in numbers at least. What we see here now is the development of pressure, black curve, due to a bearing geometry change in terms of inclination. And here we have used an inclination parameter, which is connected to alpha. It's not alpha directly, but it's connected to alpha. And it is starting here at 0.01. So there is a small inclination on the red line. You may see it. And the dimensionless load carrying capacity is just 0.0008. So it's very small, okay, dimensionless number, but the dimensional version is huge due to that it is scaled with 1 over the exit clearance squared. And the exit clearance is of the order of micrometers, very small. And therefore LCC in reality is large. And what happens then if we start this video or this animation? So we can see as the inclination increase, the pressure develop, reaches a maximum, and then it decreases again back to the ambient pressure. It's always the same, no matter the inclination, as you can see here. However, you can read from the top of this figure the value of the load carrying capacity, and you can clearly see that the load carrying capacity reaches a maximum of 0.0267, okay, for a certain value of that inclination parameter, approximately 1.2, and then it declines again. So it's not favorable to have a larger inclination, and this is irrespectively of the speed and all other operating conditions of the bearing. So, solving the Reynolds equation for a particular situation, we have to do that. We have first to adopt the pertinent form of it, and perhaps it's good enough to have the isoviscous and incompressible form of it. We adopt that. We need to define the film thickness equation. Should we include or not rigid surfaces? Should we include or not any different geometries of the two surfaces? Is it a time-dependent problem? Will this change with time? Then we should introduce the scaling parameters, and we should make the system dimensionless. And then we should execute the force balance procedure to find the exit clearance. Let us have a look at a Rayleigh step bearing, or a modified form of the Rayleigh step bearing, which you can see here is a cylindrical version of it. The specific of this bearing is such that we have a high pad and we have a low pad, and we have this at 3 different places, 3 segments, as you can see here. And the counter surface, the moving surface in this case, is called a collar, and it is the rotation of that one is caused by this spindle. And when we rotate the spindle this direction, then we drag fluid, in this case air, in over the low pad, and as it's being dragged in over the low pad, it doesn't know where to escape really. It can escape somewhat to the sides, but some of it must be dragged in over that high pad, and that is what generates the lift, as you will see in an actual physical example which we have constructed as a demonstration for you. So here is the physical example. It's a somewhat corroded steel bearing in which the spindle and collar surface weighs about 1 kilogram, and we started off to get a good speed on it. We started off by this thread, and okay, let's go. Ser ni? Luftsmörjning är möjligt. Hur fort går det då? Okej, let's go. Ser ni? Luftsmörjning är möjligt. Hur fort går det då? Fascinerande. Fascinerande. Nu börjar det. Jag tyckte jag hörde något. Nej, i helvete. Jag hör ingen kontakt
Det är
ännu.
bara, det är lite obalans, man ser axeln rör sig lite, det är lite jämvikten är inte 100.
Ja, men den kan ju också komma. I will start it now.
Okay, let's go. Se. Luftsmörjning är möjligt. Hur fort går det då? Fascinerande. Fascinerande.
So nothing is actually driving this spindle, but the inertia of the startup spin with the thread.
Det är lite obalans, man ser axeln rör sig lite, det är lite jämvikten är inte 100.
Ja, men det kan ju också komma sig av att den är ju faktiskt inte plan, va? Och då får du nu.
And now we can hear that it cannot no longer generate that film of air. The friction caused by dragging in the air over that surface was actually stopping the motion of the collar to such an extent that the velocity became too low to fully separate the surfaces. But it was carrying on that air film for quite some time, as you saw. So these bearings are possible to construct in reality, and you don't even have to have a liquid lubricant. You can also get lift with only air.